start my recording. I'm going to share my screen and we are going to get started. I'm sharing the right screen, right? Guys, you can see my the PowerPoint, right? Yeah, hopefully. Wonderful. Oh, thank you, Abby Wasta. Just wanted to make sure because sometimes I click the wrong screen. Wonderful. So we're waiting for 3 friends still. That's okay. We're going to get started with our activity for today, though. Like I said, we're going to be introducing some new vocabulary words today. So like if we're talking about steps up, most of our lessons have been sort of like half steps. Today is still it's closer to more, there's a little bit more learning today than we have been doing in the past couple weeks. It's gonna be, I think it's gonna be a good lesson though, because we're really sort of learning synonyms for ideas and concepts that we've been talking about since the beginning of this unit. And we've introduced these 2 vocabulary words, domain and range, in this unit so far. But today we're really gonna dive deep into what they mean and really see that the little tiny difference between when we connect them to input and output, because they're input and output, but they're a little bit more. There's a little bit more to them. Okay, so what I want us to start off with is I want us to think back to that dog that was attached to the leash outside of the store. Okay, so earlier in an earlier lesson, we saw a situation where the total number of times a dog barked was a function of the time in seconds after the owner tied the leash to a post and left. Less than 3 minutes after he left, the owner returned, untied the leash, and walked away with the dog. You need to think now with the context of this story and the values that we're testing here. You need to identify, can each one of these values be an input that we could plug into this scenario? Tell me yes and no. Be prepared to explain why. And can these same values be outputs that we could get? Think about when we're talking about the function sentence of barks is a function of time, what each one represents, input versus output. And decide, can all 3 of these numbers for both situations be considered inputs and outputs? I want you to take 2 minutes right now to look at these scenarios and start to make decisions. And I'm actually going to say 1 minute because hi, Ava. We're in the slideshow for today. Let's jump in. And we're talking 3, so he's only in for 3 seconds, but we're talking in terms of in seconds for that input value. And mark it as here. Okay, take 10 more seconds to wrap up those dots. 10 more seconds to wrap up those dots. Okay, so if we're thinking back to that dog leash, could input represented what was our input measure? What was our label for our input? Go ahead. Time. In what? Max? Seconds. And our output was what? Nice job there, Gabe. Our output was Max? Barks. The output was the number of barks. So now we're just talking about and looking at these numbers in the context of the story. So these could all, in theory, be plugged in here, but we need to think about it in the context of the story. Could I have an input of 15, an input of 15 seconds in this scenario? John's saying yes. Because it falls within how many minutes?
Less than 3.
It falls in less than 3. Good. Can I have 84 and a half seconds?
Yeah.
Yes, we can. This is the last one here. Can I have 300 seconds? John, why are you shaking your head no there? Very good. Because this is above 3 minutes. 300 seconds is above 3 minutes. And that's our cap. Our cap is 3 minutes on that actually that input would be this way. We only have a cap, we have a cap of 300 minutes. I mean of 180 seconds, I'm sorry. Good. Now, could each value be an output of this function? Can 15 be an output? Why? A dog could bark 15 times. Good. What about 84 and a half? Why are you saying no, Kyle? Very good. You need to think about it in the context of the story. He can't bark half the time. What about 300? Nice job, Peyton. What do we think? Probably, right? If he's literally barking every second, like, he could, in theory, have 300 barks. Good. So we're thinking about now setting caps on these values based on the scenario that we're dealing with. So now, context. I'm going to be saying that so many times today. Context, context, context. Because if you look at each one of these equations, like you can, there's a multitude of numbers that you can input and output. But now we need to look at the constraints that are given to us by the stories we're going to be dealing with. Does that make sense, guys? So we're really dealing with the context, dealing with the story, and making a choice about the values that we can plug in here, logically in the context of this story. Okay? What if I was to say, for example, what if I had an input of negative 84? What do we think about an input of negative 84? Gwen's shaking her head no. Why do you say no on that one, Gwen? Very good. This guy would be a no-go because we can't, we're not talking about negative seconds. We're talking about the time that he's in the store. So we can't go backwards on that time frame. He could, in theory, bark before you set him up, but that's not what the story is talking about. Good, nice job. This is going to be a really big part of what we're doing today. So our targets for today, we have 2 of them, okay? So we are being able to know what is meant by domain and range of a function, okay? We're going to introduce the term domain and range. We're really going to break those definitions down. Like I said when we started off this unit, I said we were going to go into them in a later point. This is that later point. When given a description of a function in a situation, we're going to be able to determine reasonable domains and ranges. So we're going to look at a story and we're going to say, logically, what are these input values going to look like? What kind of numbers can't we have? What kind of numbers can we have when we're looking at these domain and ranges in the context of the story, okay? So what we're going to be doing on slide 4 is where the directions are. You're not going to be doing anything on slide 4. So what I'm going to do is on the next slide, there's going to be a set of numbers. We have a set of 12 numbers. And we're going to have to go through that set of numbers and determine for each of the scenarios, is it a possible input for that function described? Okay? We're sorting them into either possible inputs or impossible inputs. Okay, so we're going to do one of them together, and then we're going to look at the second two independently. So let me get to that slide first, though, because I don't know what's going on here. Okay, so the numbers that we're going to be using are here. If you take, no, I don't think they're in your book. So we're going to have to be flipping back and forth between this slide here and the slide that we're going to be dealing with. Okay, so for the first one here, we're using the set of numbers to decide whether each of these numbers is a possible input for the scenario. Okay, so the area of a square in square centimeters is a function of its side length s in centimeters. The equation a of s is equal to s squared defines this function. So what we need to do is we need to go to this list and we need to determine, is this going to be a possible input for the context of this story? Yes or no. So what I need you guys to have open on your slides is slide number 6. I'm going to stay here on this slide here with the numbers, and we're going to sort them together, this first group. Okay? So what about this number? If we look at this first number here, -3. Can we have a possible input of -3? Kyle's shaking his head. Why do you think that, Kyle?
You can't have negative sign.
You can't have a negative side length of 3. Good. You can't have a negative side length. So this one's going to be impossible. I'm going to do IM underneath it because that's going to go in your impossible category. What about a side length of 25/4? Do you think we can have a fractional side length here? Yeah. I don't think that's impossible because it doesn't say anything about it has to be whole numbers, right? So I'm going to say this one's possible. So this one's going to go in your possible category. 3/5. Can we have a side length of 3/5? Yeah? I like it. Possible. 15. Sadie's saying yes. What about Gabe? Can we have a side length of 0.8 in the context of this story?
Yes.
Yes, he said yes. Very good. What about a side length of 4? Yes? Okay, very good. What about a side length of 0? Let's think logically. Can we have a side length of 0 in this scenario? We could, listen, we can, in theory, have a side length of 0. It would create a square. It would create a square that is like non-existent, but it is a possible scenario here. So we're going to say that this one is going to be a possible one because if we can have, well, it wouldn't be tangible, but like we could in theory have a square with a side length of 0 because then it would be 0, 0 to get an area of 0. What about 9? Yes, very good. Peyton, what about a side length of 1,000th? Yes, very good. What about -18? Very good. What about 6.8? Yes, possible. What about 72? Yes, nice job. So do you get a handle of what we're doing here? So now you're going to use this same set of numbers. I'm going to leave them up on the board. You're going to look at the 2 scenarios now on slide number 7. And you're going to take 3 minutes right now to sort those possible inputs based on the scenarios. So take a really close look. Think about, the second one is probably the most challenging one. You might have to do a little bit of work with that one. I want you to take 3 minutes right now to identify possible inputs, possible output, or possible inputs for the 2 other scenarios. Nice job, Ian. Okay. gonna do. Actually, no, I'm not gonna do that. So for slide. Ooh, okay. I like it. Hey, and I was talking to you, by the way. Nice job. Nice job, Peyton. Okay, we're taking another 35 seconds. Remember, do not rush. You're taking your time. If you don't get through all of it, that is okay. Hey, what I need from you, please take 10 more seconds to wrap up those final thoughts. Take 10 more seconds to wrap up those final thoughts, and then we're going to come back together. I'm going to scooch down to slide number 7 first, and then I'm going to come back here, okay? Okay, so when we look at slide number 7 here, the scenario that we have is it says a tennis camp charges $40 per student for a full day camp. The camp only runs if at least 5 students show up, and it's limits the enrollment at 16 campers a day. The amount of revenue in dollars that the tennis camp receives is a function of the number of students. So F of S, or no, actually we can say like the R of S, the revenue of like the number of students is equal, what would be like the formula in theory for this guy here? So to calculate the revenue, to get your output, you would do what?
40S.
40S, good. And we have a limit on that input of S. What does it say our limit on that input of S is? Gwen?
They have to have at least 5 students and it can't be more than 16.
So more than 5, but less than how many? 16. So we have a very sort of limited group of kids that can jump in here. So if we go back to that list and we're going to start to sort them using these criteria that they gave us, let's take a look at and start to sort these guys. What about this -3? For this scenario, would it work? No, impossible. What about 25 fourths? What does that equal to?
Equal to 6 1/4.
It's equal to 6 1/4, but why doesn't it work then, Kyle?
I don't think you can have 4 of a person.
Very good. It falls within that range of more than 5 but less than 16, but in the real life world, you can't have a fraction of a person. Good. So no fractions. If this was a fraction that equaled out to a whole number, then we could say yes. But because it doesn't equal out to like a whole number when we simplify it, it's not going to work. I don't know where this came from, the hand signals. 3/5. Once again, why? Can't have a fraction, and it doesn't fall within the range of 5 to 16. Good. 15 students. Yes. Possible. 0.8 students.
No.
No way, Jose. Impossible. So if you didn't get these written down, I would start to, on your slide, jump to 7 and copy these in. 4.
No.
No. Because why?
It's lower than 5.
It's lower than the 5. It doesn't fall within that range. 0 students.
No.
No way, Jose. 9 students. Yes, very good. Because it is a whole number. And why?
It's greater than 5.
It's greater than 5, less than 16. 0.001. No way. Negative 18.
No.
Why?
Because it's lower than 5.
Very good. It's lower than 5. 6.8.
No.
No way, Jose. What this? I don't know. No, it's a no-go. Why? Can't have 0.8 of a person. I hope you see where we're going with this. 72. No way. Why?
It's greater than 16.
Good. It is greater than that 16 max cap capacity. Good. So if you didn't get some of these matched up, please take a minute to get this written down. I'm giving you 20 seconds to get this copied out if you don't have it on slide number 7. And then we're going to look at 8. Okay, take another 5 seconds to get this copied down. And then we're moving on to 8. Okay, the scenario on 8. Once again, this is kind of a science-heavy concept, but we can still calculate it. The relationship between the temperature in Celsius and the temperature in Kelvin, so that's like another form of measuring temperature, which like Kelvin temperature is like a very sciencey sort of concept for calculating temperature. Whereas like Celsius is used like in food and all those other things. Like this is like a very purely science-based temperature system. Okay, can be represented by a function k. The equation k of c is equal to c plus so the Celsius plus 273 and 1500ths defines this function, where C is the temperature in Celsius and K of C is the temperature in Kelvin. So we're simply calculating a temperature from Celsius to Kelvin. So I want us to think about the values that it could possibly be. What were you thinking about the possible values that we could have here?
I thought all the values would work.
Okay, so he thought let me go back here. So he said all of them are possible. So slide 9. All were possible.
Kristen Bailey, please come to guidance. Thank you.
Okay. So why do we think, is there anybody here that disagrees with Kyle's idea? So everybody here put all of these in the possible category. What were the ones that you didn't put in the possible category? So everybody put them all as possible. Why are they all possible then? Adam, what were you thinking? Which one did you put any of them in impossible? Why did you say they were all possible then? Can I come back? John.
This is for slide 8.
This is for slide, 8. Yes, yes, good catch. Thank you. Why are they all possible?
As in, I just got confused.
Okay, so which ones did you think weren't possible then?
All the non-whole numbers.
Temperatures can't be non-whole numbers? Can temperatures be fractions or decimals? Kyle?
Yes.
Yes, they can. So I'm going to say no on the non-whole numbers piece. Kyle, what were you thinking here?
Since they're all technically numbers, they could all still work temperature.
Yeah, there's no area, there's no value of, like, when we're talking about temperatures in Celsius, that, like, it can't be. Like, they don't, with Celsius, they don't all have to be positive numbers. They all have to be negative numbers. They don't all have to be whole numbers. There's no restriction on temperatures in Celsius. So then if we're only adding a number to it, then our Kelvin temperatures don't have any limitations to them either. So this guy Max is correct when he says that all of these are possible. Ian, what are you thinking here? Then why don't you unmute Ian and let us know what you're thinking
I
here.
was just saying I don't think that they all work because usually temperature isn't measured in like decimals or fractions.
So temperature isn't usually measured in fractions. I'll give you that. I'll give you that much. But can you convert a fraction to a decimal? Yes. And with temperatures, when we're dealing with like Fahrenheit temperatures, we don't usually deal with decimals. That's a true statement there. And when we deal with Celsius though, because there's like a conversion like Fahrenheit converts really well to whole numbers. Like we don't really deal with Fahrenheit temperatures in decimals because there's like an equal, not like, because you're taking Celsius temperatures and you're multiplying by a value to get Fahrenheit. So like it's easy for it to be like one or the other. It's where Celsius comes in, that Celsius really is dealt with a lot of the time in decimals, because like we have in Celsius, like we have 0 degrees Celsius, right? And then we have the 32 in Fahrenheit, where like when we go to 33 degrees Fahrenheit, like it's a nice jump. And then, but because of like the number that you have to divide by to get to Celsius, it would be like 0.3 degrees Celsius. So we do deal with temperatures in decimals. I think that's where the biggest probably like misconception is, that temperatures can be dealt with in fractions, decimals, I'm sorry. When we're talking more exclusively when we're talking about Celsius stuff. So all of these are possible inputs here, because you can always have, if you have a fraction here, you can always convert it to a decimal, and then that will work with the Celsius. Okay, does that make sense, Ian? I know I'm not like a science teacher, so it's hard for me to sort of like pinpoint that exact vocab of like why we deal with things Celsius in decimals, but like most of the time, like if you watch the news, like when I was in England, I watched the news in the morning and it'd be like, it's going to be 38.6 degrees Celsius today, a high of 36 point whatever. And like, that's really hot, by the way. But because like their base unit is smaller, we deal with smaller increments with Celsius, okay? Oh my goodness, Mr. Mean. Sorry about that. So all of these values are possible when we're talking about temperature, because we can always convert those fractions to decimals and they're always going to be equal. Okay, very nice. So all of these are possible. 9. Okay, so if you didn't get this written down, you don't need to write the whole list down. You can just write these two in this box here. So now we're going to introduce a new vocabulary word that we've sort of been talking about. We're going to make some connections back, connections forward to some concepts that we've been dealing with. Okay, so let's take a look at slide number 9, where we're introducing this new vocabulary word of domain. Okay, it's not 100% new, but we haven't been dealing exclusively with it. So domain is the set of all possible input values of a function. X values, I listed some synonyms here. X values, given information, independent variables. So domain connects to inputs. What are the possible input values for the function? So we're going to be looking at domain and range, and we're going to be looking at it and interpreting what our domain is going to be based on the scenario. So like if, for example, we're talking about those 10 kids, right? We couldn't have decimals because we don't deal with inputs that are decimals. We couldn't have negative numbers because you can't have negative people. And then we're also going to deal with the sort of the sets of numbers that we have to fall within in the store. It had to be larger than 5 students, but it couldn't be larger than 16 students. Okay. So typically, domain is written as an inequality. Okay. So if, for example, when we were looking at that, the area in square feet, f of s is equal to s squared, the domain is all positive numbers. And we would write that as s, or whatever variable you're using, is greater than or equal to 0. Okay? We write domains and ranges as inequalities. For the tennis camp one, we said when we described the domain in words, we said whole number values, because we were dealing with people, at least 5, I think I meant to write, and at most 16. And so we would write that as an inequality of 5 is less than or equal to n, which is less than or equal to 16. Question?
Is there a way to address that or only talk about a fraction number, non-decimals?
Oh, okay. So the way that there is a way where but it's introduced in Algebra 2, where there's like a format. It's called function notation. I know we've talked about it in function notation, but we're writing domain in function notation where you're talking about like an uppercase W, and then you do like parentheses, and then you write it so that you know it's whole numbers. But we're going to be introducing it as writing it as an inequality and then writing like whole numbers. Because I'm not expecting you to remember all of the abbreviations where like I stands for like integers, which means like we have positive and negative numbers. We're like, I'm not going to expect you to remember like W stands for whole numbers. So we're going to write domain as like an inequality. And then if there's like a modifier of it has to be a whole number, we're going to write just that phrase out afterwards. Does that make sense? Because writing in function notation, it just requires a few more sort of remembering things that I don't want to throw in there and sort of trick you. Because like whole numbers is like an uppercase W. And then you would go like that. Or like integers would be like an uppercase I with like that. Not going to make you remember that, just modifying it by saying whole number. Good question. Questions on domain. Domain is written as an inequality, and you're adding modifiers if you need them. Okay? Okay, so now we're looking at slide 10, which is now we're looking at what about output. So we just dealt almost exclusively with input values. Now we're going to look at output values. We're going to refer to the directions from activity 1. So we're going to use the same functions from activity 1, the one with the area, and then the one with the, I think it's the one with the campers. No, the money one. Okay. So here's a graph that represents function A defined by A of S is equal to S squared, where S is the side length in of the square in centimeters. Name 4 possible input-output pairs for this function. I want you to take 1 minute right now to list out 4 possible input-output pairs, writing them either in function notation or coordinate pairs. Okay, 4 possible input-output pairs. And then we're gonna also look at, and we're gonna think about what could be our range or our possible output values. So let's take 1 minute right now to do that. Oh, that's you can write this one of 2 ways. You could say like A of blank is equal to a value, or as an ordered pair. There's a lot, there's a bunch that you could do here. Ooh, I like the second one too, so that'll be good. Okay, we're taking another 2, and then we're gonna take 10 more seconds to finalize those thoughts. 10 more seconds to finalize those thoughts. So remembering we can write this in function notation or as like coordinate pairs. So Sadie, how did you write yours? As coordinate pairs or in function notation? Coordinate pairs. Okay, perfect. So I'm gonna write 2 of them in coordinate pairs, and then 2 of them in function notation. So what was one of your coordinates that you wrote down here for possible input-output values? What was one of your pairs? 5, you said 25? Very good. Okay. Gabe said 6, 36. Good. That's another ordered pair. Now let's think about it as function notation. F of, well, actually, let me write it in with the name and the, so it's A of some value, your S, is equal to whatever your output is. So thinking about it in function notation, how could we write another coordinate pair of input output? A of, what's an input that we could choose? Adam, what's an input value? A of 4 is equal to how much? Not 15? Square it. 4 squared. You think about it, 4 times 4. 16. A of 4 is equal to 16. Who can help me with another ordered pair written in function notation? A of what is equal to what? Use one of your ordered pairs, convert it into function notation. Max.
A of 5.5 equals 31.
31. And how did you get that 31?
I looked at the line in between the 5 and 6, and it was a little bit above 30.
Yeah, but you can use that formula. 5.5 times 5.5. Get your calculator, check it. 5.5 times 5.5 is
30.25.
30.25. So 5A of 5.5 is equal to 30.25. You were given a formula here, guys. You can use the graph. The graph is good for whole number values. Use the formula if you want to be bold and use some decimal values. Okay? Because we're given both of those representations here. They both represent this function. Good. So earlier we described the set of all possible input values of A as any number greater than or equal to 0. So for this scenario before, we said area, you can always calculate the area of a shape, but it needs to be greater than, the input needs to be greater than or equal to 0. It had to be a number that was greater than 0. Now, if we think about that, what are the set of all possible output values? How could we describe all of the possible output values? Looking at this graph. If we said our inputs can never go on that side of my line, because they always need to be greater than 0, what do we know about our output values? Max, what do we know?
Our outputs all have to be positive numbers.
Very good. So outputs also have to be positive numbers. And now let's say that in a mathematical way. The way that we said it here, any number greater than or equal to 0 was what we said our inputs were. Any number S was greater than or equal to 0. How can we write that sentence mathematically? Our outputs have to be what? Our outputs will be what? Junior, what do we think? How can we write that in an equally mathematical way as it's written here for our input? So our outputs are what? So if we're saying our inputs, our F values, are any number greater than or equal to 0. This is mathematical, but we need to write it in a more mathematical way. How else could we write this? Any number. Max.
You could put that's greater than or equal to 0.
Very good. So yes, this is right. This means the same thing as what I'm trying to say down here, but I want to write it in a way that's easy to convert it to a inequality here. So our output is any number, they have to be positive numbers. That's sort of like the lay term of saying it. If we write it in a more mathematical way, we're going to say our outputs are any number greater than or equal to 0. Yes, this is correct. I like it. It's good. But we want to be really mathematical. We want to be really precise. We want to write it easily so that we can convert it to an inequality. Outputs are any number greater than or equal to 0 is a more precise way of saying it, a more mathematically precise way of saying it. I'm going to leave that up for a moment. Please get that copy down if you do not have it. Does everyone see why I'm pushing you to be more precise? Because this, you can convert this to an inequality, but this is closer to inequality language. Greater than or equal to tells me without a doubt which symbol I need to use. Greater than or equal to 0, it gives me that lower cap number. Cannot be lower than 0. Or like positive numbers, like people might forget, like, what does it mean to be positive? Like this one is more exact. Okay, so now let's take a look at the second piece of this activity. We're going to be looking at that camp one. Okay, this is where it's going to be difficult. And we're going to be looking at some output values. Okay, so number 2, but the first part of this is we're dealing now with that one with the function R, which dealt with the amount of kids that were coming to the camp and the amount of money that they were going to make. It is defined by R of n is equal to 40n, when n is the number of campers. Is 20 a possible output value in this situation? What about 100? Explain your reasoning in this box next door, number 1. Number 2, here are 2 graphs that relate the number of students and camp revenue in dollars. Which graph could represent the function of R? Explain why you made your choice. So I want you to take 2 minutes right now to determine first, could 20 be a possible output value? Could 100 be a possible output value? Then tell me why on both of those. And then which graph would you choose to properly, more precisely represent this story? Okay, take 2 minutes right now. Think about those values we said that worked for our inputs. We had a modifier on there for our inputs. Taking number 47. Yes, same constraints. We're still dealing with that same scenario. Okay, 5 more seconds. We're going to take 10 to wrap up our final thoughts. We're going to close off with a good discussion here. I'm taking your last 8 minutes and we're doing a lot with them. Take 10 more seconds to finalize your thoughts and we're coming back together. People at home, give me your thoughts on 20. Is 20 going to work for a possible output? Okay, so when we talked about our inputs or our domain for this scenario, what did we identify our domain was? There were 2 pieces that fit with this story that we said about this. So first constraint was what? Go ahead, Kyle. Can't be under 5, or what? Can't be under 5 and what? So it has to fall, and the number of students has to fall between 5 and 16. Good. That's one of our constraints. What's our other constraint? We couldn't have what kind of numbers as inputs? Adam. Decimals and fractions are no-goes. So it had to be a whole number, okay? So it has to be a whole number and it has to fall between 5 and 16. So if I have an output of 20, when using that formula of R of n is equal to 40n, and I get 20 is equal to 40n, is that a possible input? Is that a possible output? Is 20 a possible output here? No. Why? No, this would have an input of 0.5 if you calculate for the n, right? Because it's saying 20 is equal to 40 times n. Get the n by itself by dividing by 40 on both sides. 0.5 is equal to n. So to have a revenue of $20, you would have 0.5 of a student. Is this a possible output value? Why? You can't have 0.5 of a student and what? Does it fall within my range? No. Can't have half a student. You can't have less than 5. So it doesn't meet both of the constraints here. It's not a whole number, and it doesn't fall within that range of 5 to 16. You see why that one doesn't work? Now, what about this 100? Is 100 a possible output value? John is saying no. Why are you saying no, John? $100 would have an input of 2.5 people. And what is that? Why does that not work? Very good. It's a decimal, not a whole number, and it falls below that constraint of the minimum of 5 people. Do you see why these two both don't work? In order for it to be an output, it needs to meet the input constraints. Sometimes we only have one constraint, like for example, this one right here, or we might say it's just always going to have to be a whole number. This one just happens to have 2 constraints we have to work against. Good. And why doesn't it work? Because it doesn't fall within our range and we don't have whole numbers. Okay, here are 2 graphs that relate the number of students and camp revenue in dollars. Which graph could represent function R? I'm going to add a modifier to that. Which one best represents function R? Kyle, Kelly, which one are you thinking? The B or number 2? Sadie, what were you thinking? Max, what were you thinking?
2.
Junior, which one were you thinking? Okay. Junior, why were you thinking number 2? It starts at 5, ends at 16. Why else does this one best fit? Kyle Kelly. Only has whole numbers. What piece of this or what graphical feature tells me that we only are using whole numbers here? The fact that it's what, Junior? Discrete points. Very good. So when we're talking about whole numbers, our graph is going to have to look like discrete points instead of a connected line. Good, good, good job there, Junior. So that's what we're talking about for this guy here. First, we said this one fits best because it only has that the x values of 5 to 16, number 1. And we have discrete points shown by these whole number values. Does everyone see why this one best fits this scenario? Awesome. I'm going to grab another one of these for the warm-up for tomorrow. I want to jump into what you're doing for homework this evening. Okay? If you look at the assignment in classroom, I'm going to leave this up here, the words up here, because I'll come back in case you need to copy it down. Oh, Mr. Rain. Okay, so we're not going to do slide number 12. We're going to do number 12 tomorrow. So don't do anything on slide number 12. I'm going to migrate this one to tomorrow's activity. Your homework for this evening is looking at slide number 14. We have a function here. Actually, yes, I want to push you guys. I want to give you a little bit of a trickster. Or not a trickster, just a little bit more challenging. We have this function right here. It's a fraction guy. So we're going to start tomorrow off by going through this example, but I want you to take a look at it for homework this afternoon. To find out the sets of possible input and output values of this function, Claire created a table and evaluated f for some values of x. Along the way, she ran into some trouble. So she has this table here. It's going to be your job to calculate your outputs when you have these given inputs here. So you're going to take these inputs here, you're going to plug them in and calculate for your outputs for all 5 of these values. Then I want you to use the graphing technology, which means click on this link right here. It's going to take you to Desmos. I want you to graph this guy. Okay. What do we notice about the graph? You're going to tell me, what do you notice about this graph? Hint, you've never seen a graph like this before. What do you notice? Tell me here. Insert a screenshot on the next slide. Use your calculator to compute the values that you might have had trouble computing. So I want you to use a calculator to calculate these guys if you weren't able to calculate them up at the top. And then what do you notice about the computation? So what do you notice about what you have to do here? And how would you describe the domain of this function? How would you describe the domain of this function? As I said, we're going to go through this tomorrow in class. So if you're like super duper struggling, I still want you to give it a shot because I think we can. But we're going to discuss it in debrief tomorrow on this. Okay. So homework for this evening is slide number 14 and slide number 15, where you're inserting your screenshot. And then we're going to do the synthesis. I know on the lesson it says 16 as well, but I just want you to do 14 and 15 for homework this evening. Friends that have Spanish work for today, you guys are not leaving this Zoom. You're going to stay in and you're going to work on the Spanish work for today. If you have questions, obviously put it in the chat. You can start working on your Spanish work now. Friends,